Thank you, everyone, for joining me today. I know it's been a long day for every one of you. So the session for today is going to be how do we scale large models when it comes to training them through the model and data parallelism concepts. Before we can get started, just a little bit about myself. I am Shashank. I work as a machine learning engineer at Walmart. More specifically, I've been in machine learning for the past 10 years. I've worked for a variety of different companies. My scope of interest has mostly been around operationalizing a large-scale AI, be that around the personalization, recommendations, and more recently at Walmart, scaling those solutions for retail. So before we can get started with our agenda today, just to get an understanding of our audience today, how many of you have explored parallelism or are already using parallelism when it comes to training your models? Can you maybe raise your hands? Okay. We have some. So I think for them, it probably would be a good refresher of the concepts. For everyone else, this might be like a view into how to think about parallelism, what are some motivations, what are different approaches that we have in place today. And hopefully there will be a bit of a blueprint coming out of this discussion that you can use and implement in your practice. So for the agenda today, we're going to start with the motivation. Why are we having to discuss this to begin with? Then we're going to have a quick look at the complete picture of memory consumption as to how exactly or what different components are involved and how they compute or how they consume different memories. We're going to have a quick view on, before we start to talk about parallelism, what are some things you want to still take into account to make your process more efficient. Then dive into some primary approaches that are out there. And then take it from there in terms of data parallelism and model parallelism. So starting with the motivation in itself, I think for the past 10 years, we have seen a significant rise in a variety of different domains when it pertains to AI. But there are three main things that relates to the discussion today. And that is, the models have gone fatter. When you think about it from how many parameters our models are containing, they have essentially grown or perhaps even doubled every year if we were to speak it that way. Then there have been also an explosion of data. Again, a lot of companies have been collecting historical data, and now with the new invent of algorithms, to be able to use all the historical data, the size of data volume has grown significantly as well. And then last but not the least, the computational power has also increased. I think it wasn't way in the past where still machine learning development was CPU-based, but in the more recent years, we have seen a lot of inclusion when it comes to starting using GPU to train and infer the models. And so this essentially created a perfect combination of factors and an environment which has pushed the boundaries on how is it that we can train these large models when we have significant amount of data or model sizes are getting fatter. And while the computational power has gone up, there still remains a limitation when it comes to how much memory your GPUs have. So combining all these things creates an environment where it's not necessarily a privilege, but sometimes a necessity for us to explore different approaches when it comes to parallelism. Now, when we think about the memory consumption, now memory is usually the primary, I would say, the motivator when it comes to why do we want to tap the parallelism. And there are mainly two components involved in this process that essentially are memory intensive. So one of them is the data. Again, more data you have, more memory you need to use that for training your models. And then the second aspect is your model parameters. Now, oftentimes we only think about model parameters or the memory associated with model parameters as the weights, within the model that you have. But as you start to break down the entire process, there are a lot of components that are memory intensive. So yes, your weights definitely are one of them. If you have an 85 million parameter models to a billion to nowadays a trillion parameters, every single weight has a certain numerical value, and that consumes your memory. However, as you train the model, you have typically a forward propagation, and once you have an entire forward propagation, you start computing the gradients in your backward propagation, and every single gradient computation that you perform is going to consume your memory as well. Now, after each iteration, you are going to have optimizer states, which will take those gradients into account to create the next set of weights for your models to train on. And so with that, your optimization states are going to consume the memory as well. So when you think about memory consumption, yes, your data and weights are the primary components that will hold the memory, but then there are a lot of the smaller components that consumes the memory as well. And so before we jump into, okay, so now we have a model that's significantly large. We have significantly large amount of data. The very intuitive thought is let's jump into parallelism. However, if we jump right into it before optimizing our process, we would essentially be scaling our inefficiencies to n number of GPUs or the infrastructure that we would be scaling this on. So before we jump into that, it's a good practice for us to make sure that we optimize the process that we have today to begin with. And there are three main areas where we would want to optimize this process on. So the very first thing is your model optimizations. So as we speak about memory consumption, the primary, I would say the unit that consumes are your numerical values. And you can represent your numerical values in a variety of different precisions. And if you are using common frameworks, let's just say, for example, PyTorch, by default, it's going to use a single precision FP32 to train your model. So all the numerical values that are associated with all different components, they are represented in FP32. And more than oftentimes, you would not need that. In my experience, I have seen almost 99% of cases are okay if we reduce the precision of the numerical representation. So the very first thing you can do is try to use mixed precision in your training rather than the default FP32. And that does two things for you. So one is not only now you have theoretically half the memory footprint, but because your numerical representations are less precise, your computational efficiency improves. So you have a faster throughput coming out of that. The second thing you can do is also quantization. The very concept of quantization is to think about it as if you have a 1,000-dimensional vector representation, can you represent the same information without losing the performance in a more denser way, let's say 512 dimensions? So can you start to quantize your weights and activations that you have in your model? And a more aggressive way of optimization is then pruning, meaning do you really need all the parameters within all the layers that we have in our model architecture, or can you start to remove them? Now, this, again, has in practice a more of an iterative process where you would train a couple of iterations, couple of epochs, understand the performance, and start to prune. And more than oftentimes, it does come as a trade-off with the performance and the computational efficiency that you're trying to achieve. But it's still an option to explore to make sure the overall architecture is efficient. The second category is around the data and training optimizations. So the very fundamental thing when it comes to training our deep learning model is the batch size. How much data at the time we are feeding into our processor. And by optimizing the batch size, what we really are trying to make sure is that are we hitting the limits of either GPU or in some cases CPU that we have to make sure our utilization is, say, over 90%, over 95%. The second thing we can do is also around gradient accumulation. So can we try to mimic a large batch training without necessarily having to increase our batch size, and thus by also improving the throughput coming out of that. And last but not the least, do you really need all the data and the features that you have? Or is that something that you can have in the form of feature importance or in the form of less amount of data to get the similar results? And last but not the least, there are also hardware and system optimizations. So when you start to think about the actual cores or the type of processors that are being used, are you using the right framework that is compatible with those processing units that you have in place, or you're using it for your use case? And one thing that oftentimes gets overlooked as we start to talk about parallelism is your inputs and output communication overlap. So by the nature of it, think about it as you are loading your data into CPU, and as you're providing the batches to train your models on GPU, there is a communication that is going on from pulling the data from CPU into GPU. So is that communication efficient as you have set it up? So the idea here is to make sure that before we start parallelizing our training process, we want to extract every bit of it by optimizing different aspects of our architecture so that we can have the max amount of throughput we can get from a single GPU. And so then when we scale, the scale is more efficient rather than inefficient. So let's look at the primary approaches. Now, there are mainly three main categories, as you would have noticed when it comes to parallelism. The very intuitive one to begin with is a data parallelism. And more than oftentimes, you have a model that can fit on a single GPU, but you don't have, or your data that you have doesn't necessarily fit into your single GPU. And so the idea with data parallelism is quite simple in the sense where what you want is you want to replicate your models across all the GPUs that you have. So imagine you have 4 GPUs at your disposal, and the model that you're trying to train, all the parameters, all of its weights are replicated one-on-one across all of those 4 GPUs. And the data then now you have is split across all the GPUs as you train them. So the benefit of that approach is it scales up linearly when it comes to the workload that it requires to train your model. But there are also a few considerations as you think about it. So your overall memory usage, it grows as you create more and more replicas. The second thing, and this is common across any approach, is the communication overhead. So whenever you have more than one processing unit, you still need to communicate across those processing units to make sure that your training is converging in a way that you want that to be. So the communication here, and we'll see a little bit more in the future slides, is the communication of weights and gradients. So if you have, let's say, 100 rows of data, 20 rows are going into one GPU, and each of those 5 GPUs has 20 rows. Once they run an iteration, they need to communicate with each other to understand what should be my next set of weights. And this is the communication that we are referring to here. The second type is a model parallelism. So you are in a situation where neither your data nor your model can fit on a single GPU. So now you are forced to not only split your data, but you are also having a need to split your model across different GPUs. And so the idea here is your models, and if you think about it, models from 2 ways. So you have n number of, I would say, weights and parameters in a single layer, and then you have m number of layers. You can split your model by saying that the first P layers are going to be on GPU 1, the next set of layers are going to be on GPU 2, and so forth and so on. That's typically called pipeline parallelism, which we will look in the future slide. Or you would want to split each parameters or the set of parameters you have in one layer in itself across different GPUs. And that's typically referred to as a tensor parallelism. So the benefit here is that, hey, if your model cannot fit on a single GPU, you are bound to have to split the model across different GPUs. But the consideration or challenges it comes with is it's a significantly more complex than simply having a data parallelism in place. The second thing also is it introduces something that we refer to as a bubble time. So as you have different layers split across different GPUs, while certain GPUs are processing your input, the other GPUs are in an idle state. And larger your idle state is, larger your bubble size is. So the model parallelism introduces the concept of what we call to be the bubble time. And then you have hybrid parallelism, which is best of both the worlds. So not only you're splitting your data across different GPUs, but you're also splitting your model across different GPUs. And the overall benefit of that is you can use a certain amount of batching strategies to reduce your bubble time while still be able to have your training for a large model being carried out across different GPUs. Now, let's look at the data parallelism itself. I know PyTorch is one of the most widely adopted frameworks that's out there. Now, conceptually, as we discussed, the data parallelism in the nature of it is you're essentially splitting your data across different GPUs. But there are two types of parallel or data parallel approaches that the PyTorch supports. Now, data parallel is one of them, which is officially, it's not deprecated, but an official recommendation is to not use that and use distributed data parallel. And we'll look at why that's the reason. So when we think about data parallel, think about it as you have a certain mini batch of training data that you want to be trained on. So your GPU1, which acts as your master node, it takes that batch and say you have n number of GPUs available for training. It further splits that input batch into batch by n, depending on how many GPUs you have, and it passes the data to individual GPUs. They go through a forward propagation, and by end of it, computes the logic. Now what happens is once those logics are computed, all of that information is then sent back again to GPU1 to essentially compute the loss, compute the gradients, and updates the weight. So in this scenario, your GPU1 somewhat acts as a master GPU, which controls how the data is been collected, is been distributed, and then what needs to be the second set of updates that needs to happen. The other approach, which is a recommended approach, is the distributed data parallel. So the idea here is that no single GPU is acting as your master GPU. So when you think about it, your effective batch size, so let's say in the data parallel, your batch size was 2048. Now in this case, you cannot necessarily use the same batch size because in that scenario, your 2048 batch size was getting divided by n number of GPUs you have. So in this case, your effective batch size is going to be by n, so that GPU can handle that much amount of data. But all of the batches are fed individually to a set of GPUs that you have. Now they go through the same forward propagation and computes the logic towards the end. Now by end of it, there are different all reduce operations. Now what all reduce operations are is essentially your way to communicate different losses and gradients that have been computed across different GPUs and what should be my next set of weights. That's in an essence an all reduce operation is. So there are different strategies you can start to look into when you consider how the all reduce operations can be computed. But in this scenario, there's no bottleneck of a single GPU acting as a master, and they're all operating individually with the batch of data that is being fed into them. Now, briefly touched upon the all-reduce operation. So let's try to look into a little bit detail on what it is essentially. So the very basic idea behind all-reduce is that you have a batch of data that is getting trained across different GPUs. They are not talking with each other, so they don't know by end of my first iteration what should be the next set of weights that I need to update my model parameters with. And this is where the all-reduce comes into play. And there are different strategies that you can have in place depending on how you want to optimize the communication that happens to communicate those gradients across GPUs. So one of the common approach is the ring all-reduce. So the idea here is that, say you have 3 GPUs. Now, each GPU collects the information from a previous GPU, if you were to assume them to be in a sequence. It reduces, or it performs a reduce operation on that collected information, and then passes on to the next. And so once all of the reduce operations are performed, is then what happens is an all-gather operation where all of the reduced chunks from individual GPUs are collected and then circulated across individual devices that you have. So the idea here is a sequence, pass of data from one GPU into another, an all-reduce. Once all reduces are performed, you do an all-gather operation. The second approach is a tree-based approach. So the idea here is that conceptually, from a tree standpoint, every leaf or every device, if you were to imagine, they passes their data to the parent. And so once the data is received, there's a local reduction that happens. Once that happens, it pushes up to the further parent. And once the overall propagation is back to the root then broadcasts the entire reduced operation across all the GPUs. So the idea here is that if you think about it, there are certain operations that can happen in parallel because it's not happening in a sequential essence. And the third approach is a hierarchical all-reduce. Now, so far, the way we have been discussing or describing this distributed approach is still conceptually a single node multi-GPU setup. Now, you have situations where either that is not possible for both in infrastructural reasons or the architecture that you have in place. So in some cases, you have a multi-node, multi-GPU as a setup. And this is where the hierarchical all-reduce comes into play. So the idea here is that each node can have its own individual all-reduce operation, that how you want to carry it out. But then you have a representative node across different, or rather a representative device across different nodes to then communicate these gradients across different nodes that you have in place, and then for that representation to then broadcast the information across all the GPUs across every single node. So there's 2 types of all-reduce that is happening in this scenario. One is an intra-node operation, which is happening within the single node, and then you have an inter-node all-reduce. And once those 2 things are done, you have an intra-node all-together operation broadcasted by the representation device. Next we have is the types of model parallelism. So again, you're in a situation where you essentially have to use a model, or the problem that you're trying to solve requires you to have a significantly large sized model. Or sometimes what we have also seen in practice is that in theory, yes, the more advanced GPU that are out there has 80 GB RAM, but more than often time you may not even have that available on your team, and you are bound to use a smaller GPU. So even if your model hasn't increased because of the limitation on what GPUs are available, you may have to adopt to the model parallelism. So there are essentially two types of it. So one, we call it a tensor parallelism. So this is where you are essentially not necessarily splitting different layers, but you're manipulating two types here. So either you are splitting a row-wise split, which is your input split, or you're doing a column split, which is kind of, or perhaps a column split, which is your input split, and then the row, which is an output split. So think about it as, in this case, you have kind of three different nodes within the layer. Now you can have the first node going into GPU 1, the second into GPU 2, and third into GPU 3. And you can do that from both input as well as output perspective. And what you have is a pipeline parallelism. So the idea here is that you are essentially splitting layers in the sense where your, let's say, first 3 layers are going into GPU 1, the next set of 3 layers are going into GPU 2, and so forth and so on. And so this is where, in practice, it's a relatively simpler to think about pipeline parallelism than to think about tensor parallelism. But there have certainly been a lot more packages that have come up. One is the Megatron from NVIDIA that does really good with the tensor parallelism. But when you start to think about model parallelism, what you get into is something along these lines. So if you look at it on your left-hand chart, so the idea is, as you start to input the batch of data, your first n layers are going to be computed, say, by GPU 0. And so while those computations, as in the forward loop, is happening, your GPU 1, GPU 2, and GPU 3 might be in an idle state. And so the data needs to propagate across all the GPUs. Once the data has propagated, you have a backward propagation that's happening, and a similar cycle continues. And so the white spaces that you are seeing is what you can call it to be a bubble time. So you have a situation where your GPUs are staying in an idle state and can impact your overall throughput that you can get from your system. So there are different strategies that are being looked into. One is a micro batching. So what you are essentially doing is you are further batching your data into a form where, imagine you're flooding your inputs with small micro batches. And while initially there's a ramp-up time, at some point you will have a pipeline that, while batch 4 is forward propagating on GPU 0, batch 1 is already on GPU 3. And so you can imagine your bubble time reduction. So the idea here is to minimize the white space that you are seeing. So there's a ramp-up time that's involved, but by batching, you can start to minimize or alleviate what that bubble time is. Now, last but not the least, you have hybrid parallelism. So again, the idea here is not only you are doing a data parallelism, you are also doing a model parallelism, and within the model parallelism, you are doing both pipeline parallelism as well as tensor parallelism. And oftentimes, this is referred to as a 3D parallelism. Now, not every open source framework allows you. One of them is the NVIDIA's Megatron LM that I referred to earlier as well. So think about it as you have 3 different parameters, your T, P, and D, where your T is essentially your tensor parallelism parameters. How do you want the tensors to be split? Your P is going to be your pipeline parallelism. So how do you want to split the layers across different GPUs? And your D is going to be your data parallelism parameters in terms of how much or how many replicas you want to have in terms of parallelizing the data itself. And so I think we're at the time here, but I want to end with some common frameworks. Again, for majority of general purpose use cases, You have PyTorch, which supports both distributed data parallelism as well as the form of model parallelism in the form of fully sharded FSDP. You also have a similar support from the TensorFlow framework. You have Horowitz, which essentially is, I would consider it to be a wrapper. So it integrates well with open source tools or frameworks like PyTorch and TensorFlow. But the idea here is more so much about optimizing all reduce operations. So there are, again, a variety of things that I haven't had a chance to go into detail. But the all reduce operation oftentimes is the computational bottleneck. And Horowitz has different ways of tackling that. So it's a wrapper. I would consider it as a wrapper on top of that. Then you have DeepSeed, you have Megatron LM, you have Mesh TensorFlow, and so forth. So there are a variety of frameworks out there. I think try to pick one that fits to the approach that you have, fit to the processing unit you have, and overall the integration within the system itself. So yes, thank you so much. That was me.